Continuing on with some sampling distributions and analysis, we're actually going to combine some binomial ideas in this lesson as well. So we have a coin and we want to figure out how many heads we would have to get out of 30 tosses in order for us to be worried that a coin is unfair. So let's review a little bit of binomial theorem. So X is going to be the number of heads, successes that we have, and X is a binomial random variable, bins, from lesson 5.4. So binary, the B is for binary. So do we have two outcomes? Yeah, it can be heads or tails. I, is it independent? Does the probability on the second throw, is that affected by the outcome of the previous throw? No, every time you flip it, it's the same probability, which is actually S. N is, do we have a set number of trials? Yeah, we have 30 tosses that we're going to be looking at. And then S, are they the same probability every time? And what is it? Yep. And it's 50% heads, 50% tails. So the formula for the mean of a binomial, mu, is going to be N, the number of trials, times P, the probability. And we discussed how that would be equal to those 30 trials times the 50%. So our mean is that we should expect 15 heads. And that's what we're going to say for our interpretation here, is that we expect, on average, we can expect to get 15 heads out of 30. We should probably, I'll learn how to type one of these days. 15 heads out of 30. So then we want a formula for standard deviation of our binomial here. So I'm going to write it down again. So we got our standard deviation. Sometimes we say that is sigma there. It's going to be the square root of n times p times 1 minus p. So that same n and p, and now we're just introducing 1 minus p, so that's going to be the probability of not getting a head, so the probability of getting a tails. So this will be equal to 30 times 0.5 times 1 minus 0.5. So remember, 1 minus 0.5 is just going to be 0.5. And this will get us 2.74 when we type that into a calculator. So we can say there, to interpret that standard deviation, what does that standard deviation mean? That means that the number of heads will typically vary from the mean of 15 by 2.74. So in one standard deviation away from 15, 2.74 on either side. Remember, outside of 2 standard deviations away from the mean, that's where it gets unusual. So that may come in handy. So if we're in class, if you're doing this in class, maybe you'll toss it 30 times. Maybe your teacher lets you touch things in class, manipulatives, whatnot. I don't. You do it 4 times, maybe 5 times, write them all down, record all your values on a sticker sheet, put them on a post in front of the room, and then jot down a dot plot there. I don't have you. You're on video. You're in the future. I'm in the past. So I'm just going to head over to Stapled.com and generate the dot plot that my class has done in the past. So be right back. Hi, I'm up here now. So I collected my data here and threw it down. I even threw this, the summary statistics as well, so you could see anywhere from 10 to 22 heads out of 30. So this is a sampling distribution of X, which is the number of heads out of our 30 trials. And next we want to say, what is the approximate shape of our sampling distribution? You can tell it kind of has a little bit of data up to a peak and then kind of goes back down as well. We can say this is symmetric, or we want to say normal. We want to say this is a normal distribution. And we actually have a way to check this as well mathematically, and we call it our large counts. So what we do with the large counts is we see, is n times p greater than or equal to 10, and then is n times 1 minus p greater than or equal to 10. So I'm going to jot this down, so that's why my face got a little bigger. So we want n times p, is that greater than or equal to 10, and is n times 1 minus p, is that greater than or equal to 10. So remember, our n is 30, our p is the 50%, and we want to check to see if that's greater than or equal to 10. our n is 30, 1 minus the 50%, or 1 minus 0.5. We want to see if that's greater than or equal to 10. And they both are. We already did n times p and found that's 15. And this will also be 15 because it's 0.15 as well. So what these are, these two numbers, these 15s, they are the same because we have the same probability, 0.5 and 0.5. But what those represent are the expected numbers of successes on the left and failures on the right. So in this case, heads or tails, but successes or failures there. So that's our large counts. We're going to jot that down, how to do that again on the next page in our final wrapped up notes. So let's think of this sampling distribution as a normal distribution, which we just checked a couple different ways. Graphically, it looks normal. And then when we did our large counts, that is normal as well, since both of those are greater than or equal to 10. So we're going to use the mean and standard deviation from number 1, which we have up here, 15 and 2.74. And we're going to draw a picture and find the probability of getting 19 or more heads. So if you recall from first semester, we have our normal distribution looking line. So I'm going to go to the line tool and hit shift to make sure it's perfectly horizontal. And then I'm going to draw in and sketch a approximate normal distribution curve. Just a little off my line. Let me move the line so it looks a little bit better, maybe. Oh, I went away. Oh no, killed myself. What have I done? Show me. I'm gone. Camera settings. No, what have I done? No, everything's going away. Ah, good times. And then we're going to insert a vertical line there once I figure out how. Insert a vertical line there right in the middle. That'll be our mean. I want to make sure it goes all the way up there. So that'll be our mean of 15. And we'll just jot that in. And then we want another vertical line where 19 is. So 19 is probably to the right somewhere. Let's make sure it's vertical. There we go. And we're going to shade that in because that's what we're curious about. We're curious about this side over here. We want that 19 or more. And then one final thing before we wrap up our drawing here is we want to say this is a normal distribution. So we say capital N. And then we want our mean, mu 15, and then our standard deviation, sigma 2.74. So I'm going to jot in there that this is mu and standard deviation there. So in order to draw a normal curve, we want to see, I don't know why I'm still gesturing like you can see me. We want to see that n for normal distribution, the mu for 15, and then this sigma there for our standard deviation as well. So we're going to find the probability of getting 19 or more heads. This might take some of y'all back, where we are going to be looking at z-scores. I'm going to get off pink here. We're going to look at z-scores. So z is equal to x, our value that we're comparing, minus mu, our mean, divided by sigma, our standard deviation. So we are looking at an x value of 19. Our mu is 15, and our standard deviation is 2.74. And when we subtract and divide and make sure we round to 2 decimal places for our z-score, remember z-scores are 2 decimal places, we get 1.46. So then we would go to a table A and we'd find the area, and we want 1 minus that area that we are given for 1.46. Because remember, when we look at table A, it's giving us, if we're looking at 19 there, or in this case 1.46, it's giving us the shaded area to the left. We want the other side of that. We want the shaded area to the right, because we're looking at to the right there. So we want 1 minus 9.9279, which is what we would get from table A. And we'll see more of this in the future as well. And this will give us 0.0721. So if we kind of round that to a percentage, 7.2%. So with 19 heads out of 30, would we have convincing evidence that the coin is fair? What we've been talking about the last class or so is that we're going to compare that 7.2% to 5%. And that is greater than 5%. So that tells us that this is not statistically significant. So we don't have convincing evidence that the coin is unfair. Which hopefully coins aren't unfair because, they're coins, and we've always believed that 50% of the time it lands heads, 50% of the time it lands tails. So let's wrap up with some important ideas from the text on the next page. And we're basically going to wrap up kind of what we just did. So in order to find the mean mu, I'm going to jot that down in a second, we just do n times p. To find the standard deviation, sigma, we do the square root of np times 1 minus p. I'll draw all those in there. Now, how do we interpret the standard deviation? So standard deviation interpretation is that the number of whatever we're talking about, typically varies from the mean of whatever the mean is by whatever the standard deviation is. So I'm going to kind of scoot that over a little bit. And I'm going to fill in my blanks here. So I want my mean is mu, my standard deviation is sigma, and this is the square root of all that. And this is the number of whatever we're talking about varies from the mean of whatever mu is by the number for whatever standard deviation is. We got two more things here, so hopefully you left some room. The first one is our large counts condition. So we're checking to see if n times p is greater than or equal to 10. I'm going to write in that equal to sign in a second. And we need to make sure that n times 1 minus p is also greater than or equal to 10. So we got to check both those things. And if they are, then the sampling distribution is approximately normal. And we can use stuff like z-scores and table A, etc., like we're about to use on the third section of this box. And that like we used earlier. And in class, we'll show you where to find a table A again, because I believe you might need it. Yep, number 3 there on this page. So that's our large counts condition. I'm going to zoom in a little bit for y'all to see. There we go. Now we can see a little bit better. And then finally, we want to talk about our z-score and how to use table A. And we'll practice this again in class and over and over and over again. We'll even go to the calculator, and Staplet as well can do it all fantastically. So we have a z-score is our x, whatever our x value is that we're usually given in the problem. And our mu and standard deviation, we know what that is. And then we'll use table. That's not how you spell table. We'll use table A. In fact, why don't I just type that out for you? That seems way better. So with z-score, we'll use table A. And I do want to mention that x is the value given, usually in the problem, whatever we're talking about. So for the last example on the first page, we talked about here, it was the 19 heads, probably again 19 heads out of the 30 trials. So with this, you'll go and practice with, on this page, application 6.3, working groups. We'll show you table A, It will go to the calculator as well and remind you guys where to find how to use how to use z-scores and how to find these probabilities that we're asking for of normal distributions on the calculator as well. If you want, you can go back to the videos over chapter 5. I think there's a few of them that will help remind you of those as well. All right, take care.